Okay, up till now, everything we've talked about in terms of transporting something in and out of a cell would be passive transport. Free to the cell along the concentration gradient. But there are times when a cell needs to basically pump water uphill to basically pump these molecules or atoms against their concentration gradient. And so it's what we call active transport. It's a good example is the sodium-potassium pump.
Active transport is a type of cell transport that requires the input of energy in the form of ATP. The proteins that conduct this form of transport are often called pumps because they force molecules or ions to move from an area of low concentration to an area of high concentration. This is commonly referred to as against the concentration gradient. One of the more common examples of active transport is the sodium-potassium pump. The job of the sodium-potassium pump is to move sodium ions, or Na+, out of the cell, and potassium ions, or K+, into the cell. Let's take a closer look at how this happens. The sodium-potassium pump has binding sites for 3 sodium and 2 potassium ions. Let's follow the movement of the sodium ions first. After 3 sodium ions are positioned within the carrier protein, an ATP molecule is split, releasing phosphate. This phosphate binds to a location on the exterior of the carrier protein, causing the protein to change shape. As the protein changes shape, the 3 sodium ions are released to the other side of the membrane. Next, 2 potassium ions position themselves within the carrier protein, causing it to undergo another change in shape. In the process, the phosphate molecule is released. Once the phosphate molecule is released, the carrier protein expels potassium ions into the interior of the cell. The carrier then resumes its initial shape, completing the cycle. Notice that for every 3 sodium ions leaving the cell, 2 potassium ions enter. Since both sodium and potassium ions have a positive charge, this unequal movement causes an electrical gradient to develop across the plasma membrane of the cell. A number of cellular processes, including the generation of nerve impulses, use this electrical gradient.
So I don't know if you can hear this narration. I'm thinking maybe you can't, but big thing it is. I just turn it down just in case you can't hear it. So it involves a protein pump. It involves moving these ions against their concentration from a low concentration to a high concentration. Right? That's very different than what we've looked at till now. We see this binding site on the protein that is for ATP molecule, adenosine triphosphate. Okay, it comes in. Let's see here. Breaks off one of the terminal. It breaks off the terminal phosphate. The energy from breaking that bond is transferred to the protein. The protein changes shape, pumps the sodium in. Potassium rushes into the pump. There's 2 sites on the protein where potassium has an affinity for. It changes back to its original shape. The potassium is pumped to the inside. Okay. So what we see is we end up building up, as the video says, it makes a electrical gradient. Okay, and that electrical gradient is actually what causes our nerve cells to fire. It's basically the electricity for our nervous system. So active transport against the concentration gradient. Okay. So there's a section in your book about electrochemical gradients. So we have a chemical gradient. Obviously, there's more potassium inside than there is out, more sodium and chloride on the outside than in. Why do none of these molecules move across the gradient or across the membrane easily? Because they're all charged ionic compounds. They need this protein to move through. Okay. So the electrical chemical gradient is all of these things combined. Right? This molecule is going to tend to want to move out because it's a negative charge. It's going to want to move towards the opposite charge. On average, the positive sodium ions are going to want to move inside, right? According to the electrical gradient. According to the chemical gradient, it would also want to move inside. For the potassium, however, electrically it's happy where it is, but chemically it should be moving towards the outside to decrease the concentration. So this can get pretty complex pretty quickly. Different types of transport proteins, depending on whether they transport one or uni molecule or ion, whether it's sim or collectively or at the same time, transporting two molecules in the same direction. An antiporter is a protein that moves two different molecules through the membrane in opposite directions. Okay, it's like an antiporter. More vocabulary. Okay, we'll look at this. Active or passive transport? Okay. Well, we see it's active because we see this ATP. That's the energy being used. And what are we moving here? We're moving potassium in, and we're moving sodium out. Well, that's the video I just showed you about moving sodium and potassium. Basically what we're doing is we're maintaining an electrical chemical gradient across the membrane so that these ions can flow through the membrane and cause an impulse. Active or passive transport. Oh, we don't see any ATP here. Okay? So at first, your first gut would say that it is passive transport. But the thing is, in this case, the movement of this large-ish molecule, glucose, and again, if we go back to here, we're going to remember glucose is not really, the membranes are really not that permeable to glucose. Right? They move through begrudgingly, but it takes a little bit of energy. So here we are, and glucose has moved a lot. It's because it's a pretty big molecule, and it is fairly polar too. The movement, the energy that stimulates the movement of glucose, in this case, into the cell from the extracellular side to the cytoplasmic side, is actually the movement of these other molecules. And this gradient, electrical chemical gradient, is caused by active transport. So the cell uses energy to pump these charged particles outside of the cell. They're pumped against their concentration gradient. They build up outside. What do they want to do? They want to get inside. They can't go through the membrane. So what do? They flow through this protein, this big yellow protein. It's like a wheel. And as they flow through, the energy from that is used to move the glucose too. It's called co-transport or secondary active transport. It's not primary because the ATP is not being used directly by the protein. Another protein is using ATP to pump these sodium ions out. And because they build a gradient and they want to flow through, that's the energy used to transport the glucose. Okay, co-transport. Alright, finally, this is, I think, the last few slides is about moving large, again, the theme here is movement of things in and out of the membrane. And here is our large molecule. So if we go back to that diagram, well, let's just do it real quick. Yeah, this one here. Yeah. Large and uncharged molecules. It's hard for them to move through the membrane. So they're going to need a little help. They're going to need some active transport, a little investiture of ATP. The way this happens is it's called endocytosis, or into the cell, into the cytosis. Here's your large particle. Here's some liquids and small particles. Phagocytosis, Phagocytosis. This pertains to large particles. They are enveloped by the plasma membrane, which does take ATP. It's not shown here. This is active transport, though. And then the molecule, and inside of this vesicle is brought inside the cell. If we're talking about the liquid and the small particles, same process, a little invagination of the membrane, the small particles go in there, the vesicle is formed, and this has been transported inside the cell. If it is small particles and liquids, it's called pinocytosis. Okay. And then lastly, here is a different form. It's similar in a way to the idea of a protein pump, but here the protein that's involved is a receptor. It's on the outside of the cell. When all of these receptors are filled with whatever molecule it is that fits three-dimensionally into the receptor, here these receptors are for the star-shaped molecule, and once those molecules are received in the receptor, that forms the vesicle and is brought inside the cell. So this is kind of just a more selective way of moving things in and out of the cell through endocytosis. It's specific in that the blue squares do not fit into these receptors. These receptors are specifically for the star-shaped molecules. Okay. Exocytosis, just the opposite. We take a vesicle from the inside, containing liquids, containing solids, containing whatever, and it moves to the to the outside of the cell, and that contents are burped out into the extracellular matrix. So, movement of things in and out, passively, actively, simple diffusion for some molecules, osmosis when we're talking about water moving through a semi-permeable membrane. We've got active transport to move charged particles, to move big particles. We have pumps that use ATP to change shape and move things. We have electrical chemical gradients, which is again the combination of gradients in electrical pulse of electrical charges, and also to do with the chemical gradients. And so that really concludes the information on this first exam. And so email me if you have issues.